Okay, so today we're going to talk about 5.5, which is the last section in chapter 5. And this is all about complex eigenvalues. So eigenvalues are complex numbers. And we're going to start our discussion by looking at this matrix A, which is 0, 1, minus 1, 0. So let's look at this matrix. 0, 1, minus 1, 0. Let's remember for a second what this actually does. So notice that A times E1 is 0, 1, minus 1, 0 multiplied by 1, 0, which is 0 plus 0 and 1 plus 0. So 0, 1. So 1, 0 gets sent to 0, 1. So 1, 0 over here gets sent to 0, 1, right up here. A of E2 is 0, 1, minus 1, 0, 0, 1, which is 0, minus 1, and then 0, 0. So E2 gets sent to over here to negative 1, 0. What this actually is doing is taking everything and rotating it 90 degrees clockwise, counterclockwise. So that's what this matrix is doing. So in terms of the eigenvectors and eigenvalues, a rotation, if we rotate 90 degrees counterclockwise, well then there are no vectors which end up being a scaled version of where they started. Because after we rotate, every vector changes directions. Which means if I said find the eigenvalues and eigenvectors, you wouldn't find any. Right? And let's just see what happens when we try to do that. So if A was 0, 1, minus 1, 0, and we tried to find the eigenvalues and eigenvectors, we'd look at A minus lambda I. And so A minus lambda I is minus lambda, 1, and minus 1 here. Take its determinant, and we get minus lambda times minus lambda, minus 1 times minus 1. So that's positive lambda squared plus 1 is 0, which says that lambda squared is negative 1. And so we get no real eigenvalues. But if we consider this as an equation in complex coefficients, well then we do have eigenvalues. I can say that lambda is plus or minus I, because I squared is negative 1. And what we're going to discover in this section is that anytime we end up with complex eigenvalues, really what's happening is we have some sort of rotation going on. There's a rotation hiding inside the matrix transformation. There might be some other stuff, some other scaling, and some other stuff where we take the square and turn it into some parallelogram. But then we have some rotation, and the rotation is what causes us to have no real eigenvalues, and therefore no eigenvectors. But we can think about what's going on in terms of the complex eigenvectors and eigenvalues as well. And so after finding our eigenvalues, in this case they're imaginary, we can still ask for eigenvectors. And our eigenvectors are also going to be complex vectors with complex entries as well in this case. And so let's go through that process. Let's find an eigenvector corresponding to each of these eigenvalues. So if lambda is I, so A was 0, 1, minus 1, 0. And let's say that lambda is I. Then what we're looking at is we're looking at A minus I times I, imaginary I times the identity matrix, which is negative I minus 1, 1, minus I. Now, we could row reduce this. Actually, this one is a little bit tricky to row reduce. These i's that end up being in here really do make for some trouble as far as row reducing these matrices. This one wouldn't be so bad, but we'll see some in the future that are trickier. So let me point out a trick that allows us to make things work a little bit easier. We know that I is an eigenvalue, which means that we know that we must have an eigenvector, which means we know we must have a non-trivial solution. which means we know we must have a free variable. So this system becomes negative I x1 minus x2 is 0, and x1 minus I x2 is 0. But we know that we have a free variable because this system has an eigenvalue, so therefore it has an eigenvector, so therefore the system has a non-trivial solution, so it has a free variable. So let me look at equation 2 here. This becomes x1 is I times x2. Suppose that x2 is our free variable. Since we must have a free variable, we can pick x2 to be our free variable. If x2 is a free variable, we can pick x2 to be anything I want. So suppose that we let x2 to be 1. That's a pretty simple thing to let x2 be. If x2 is 1, then that means that x1 is equal to I, which means that my eigenvector will be I1. Okay, now let's just check this, just to convince you that this works. Right, so what happens? We want to check to make sure that this works, so I want to check that A times I1 is equal to lambda times I1. So I want 0, 1, minus 1, 0 times I1, and that had better equal lambda, which was I, times I1. Well, this is 0 and minus 1, so that's minus 1. This is I and 0, so that's I. When I push this through, I get I times I, which is minus 1, and I times 1, which is I. So in fact, it works. So for lambda equal I, the corresponding eigenvector is I1. Let's try our other one. So lambda equal I gave us V is I1. So our other eigenvalue was negative I. To find the eigenvector corresponding to this, we'll look at A minus lambda I, which is A plus I, which is I on the diagonals, minus 1, 1. And we're going to do the same thing. We're going to think about this as I x1 minus x2 is 0, and x1 plus I x2 is 0. We can use either of these equations, it doesn't matter. Now let's look at the first one, just because we get positive numbers. I get I x1 is equal to x2. Since we can assume that x2 is free, I can put anything I want here. So that means that if let's let x2 equal 1, just because 1 is nice, that tells me that x1, that I x1 is 1, but if I x1 is 1, then x1 had better be negative I, because I times I is negative 1, and we need that negative to cancel out to get 1, which means that our vector is x1, x2, which is negative I, 1. So that's the eigenvector corresponding to the eigenvalue negative 1. Let's look at another one. All right, so let's look at this matrix. Let's find eigenvalues and eigenvectors. So we're looking at A minus lambda I, taking its determinant. 1 minus lambda, 3 minus lambda. 1 minus lambda, 3 minus lambda, minus 1 times minus 2, which is 3. Minus lambda minus 3 lambda is minus 4 lambda, plus lambda squared plus 2, which makes lambda squared minus 4 lambda plus 5, which is lambda minus 5, lambda minus 1. Nope, it's not. That's the whole point. Right? That doesn't factor that way. The whole point is that, in fact, this doesn't factor, because if I tried to apply the quadratic formula, I'd get negative b plus or minus the square root of b squared minus 4ac, but b squared is 16 and 4ac is 20, so I actually end up getting a negative under the square root. So if I set this equal to 0, I get lambda is equal to negative b, which is 4, plus or minus the square root of b squared minus 4ac all over 2a, which is 4 plus or minus the square root of negative 4 all over 2, which is 4 plus or minus 2i all over 2, which is 2 plus or minus I. And this illustrates a fact that's always going to be true. When we have a complex eigenvalue, it's always going to, the conjugate, that is changing the sign of the imaginary part, is also always going to be an eigenvalue for the same system, because these eigenvalues show up as solutions to these equations. Right? So if lambda is an eigenvalue, the conjugate of lambda is also an eigenvalue for the system as well. So we have two eigenvalues, 2 plus or minus I. So we have lambda equal to 2 plus or minus I. So let's find our eigenvectors as well. Let's start with lambda equal 2 plus I. If I start with 2 plus I, and I looked at a minus lambda I, what I get is 1 minus 2 plus I, minus 2, 1, 3 minus 2 plus I, which is minus 1 minus I, and 1 minus I. If we convert this to a system of equations, it becomes minus 1 minus I, x1, minus 2 is 0, and 1, x1, plus 1 minus I, x2 is 0. We can pick either of these equations to work with. Again, let's just stick this with the second one, and we see that x1 is negative 1 minus I, x2. If x2 is free, we can choose it to be anything we want. We will look at some where it makes sense to pick something other than 1, but for right now, let's just pick x1 equal to 1. And if that's the case, then x1 is negative 1 minus I, which is negative 1 plus I. So we get from these that x1, x2 is minus 1 plus I, 1. Right. So from our eigenvector, eigenvalue that we started with, we ended up with this eigenvector. At this point, we'll come back and look at this matrix for a later example, but for right now, finding the other eigenvector corresponding to the other eigenvalue is a similar practice, and we're going to move on to something that looks a little bit different. All right, so we'll look at this one and ask the same types of questions. What are the eigenvectors and eigenvalues for this matrix? So this matrix has some decimals in it, but we're going to work with it exactly the same as before. So this should be a 0.7. So we look at, to find the eigenvalues, we'll look at a minus lambda I, 1.52 minus lambda, 0.4 minus lambda, 0.56 minus 0.7. When we take the determinant, we get 1.52 minus lambda, 0.4 minus lambda, minus 0.56 times negative 0.7. And so this is 0.608. If I multiply these, I get minus 1.52, and then another minus 0.4, which is minus 1.92 lambda, plus lambda squared, plus 0.392. And that's pretty convenient because 0.608 plus 0.392 is 1. So I get lambda squared minus 1.92 lambda plus 1 equals 0. And again, we see that this is going to have no real solutions because b squared is less than 4, but minus 4ac is going to be bigger than, will be 4. So I'm going to have a negative under the square root. So no real solutions, but it does have some complex solutions. So if we apply the quadratic formula, we get negative b plus or minus the square root of b squared minus 4ac all over 2. And that becomes 1.92 plus or minus the square root of negative 0.3136 all over 2. And this becomes 1.92 plus or minus 0.56i. The square root of 3136 is 0.56i all over 2. And so now we get our 2 eigenvalues. We get lambda is 0.96 plus or minus 56 is 28.28i. So there's my eigenvalues. Let's find an eigenvector. Let's actually find both of these eigenvectors. So if I started with lambda is equal to 0.96 plus 0.28i, this becomes a minus lambda I, which is 1.56 minus this eigenvalue. Which simplifies to .6 minus 0.28i, 0.56 minus 0.7. This will become 3.92, 3.04 minus 0.28i. And so this system of equations reads 0.6 minus 0.28i x1 is minus 0.7 x2 is 0, 0.56 x1 plus 3.04 minus 0.28i x2 is 0. Let's again go with the second equation. I get 0.56 x1 plus 3 is equal to negative 3.04 minus 0.28i x2. And so now's where it makes sense to pick an x2 which isn't just 1, mainly because of all of these decimals. So in this case, I can divide by 0.56 to get x1 is negative 3.04 divided by 0.56, which is divided by 56 over 100, which is divided by 56 times 100. Minus minus makes plus 0.28 divided by 0.56, and that's all times x2. Which becomes, if I multiply by 100, I get 304 over 56 negative plus 0.28 divided by 0.56 is 1/2 all times x2. So I have x1 is equal to this. Now we can pick our x2 to be whatever I want. So the easiest thing to pick here so that we don't have any fractions or decimals left over would actually to pick x2 equals 56. Because if x2 is 56, when I multiply through, then I get x1 is negative 3. That's supposed to have an I there, sorry, I. Then I get x1 is equal to negative 304 plus 56 times 2 is 28i. So that the eigenvector is negative 304 plus 28i, and then 56. And again, finding the eigenvector for the other one is similar. It just comes down to picking the right thing so that we don't have any decimals or fractions left over. And finally today, we'd like to discover the hidden rotation that's inside of the transformation given by multiplying by a matrix with complex eigenvalues. So this is a matrix that we saw earlier. We calculated the eigenvalues. In fact, we found 2 plus or minus I. And we calculated the eigenvector, v corresponding to 2 plus I, and found that this was the eigenvector. And so here is my claim. We're going to make this matrix, which I'm going to call C, and it's going to be P inverse times A times P, where P is a matrix that's constructed out of the eigenvector, the complex eigenvector that we get really from either of the complex eigenvalues. Remember that the eigenvalues are complex conjugates. If we get 2 plus I, we get 2 minus I as well. In fact, the other eigenvector would be the conjugate of this, and it would be minus 1 minus I and 1 as well. In fact, we can use either of these, but since we found these, let's use this. P is going to be the real and imaginary part of the vector v. The real part of this vector is minus 1, 1. The imaginary part of this vector is 1, 0. So all that I did was pull this off into 2 pieces. I no longer have any i's, right? But I just pull off the real numbers and then the coefficients in front of I, and I use that to make the matrix P. All right, so then let's just work that out. In this case, what we actually get, I'm just going to use a calculator to figure out what C is. So if we calculate, I stored P, I stored A, I'm just going to calculate P inverse times A times P. And this is what I get. Now, my claim that this matrix C that we've discovered here is in fact a rotation matrix, in addition to some scaling, but it's essentially a rotation. We got a rotation and then also a scaling matrix. Let's see why that's true. So I'm going to draw a little picture, a little triangle, some trigonometry. We're going to look at A, B, so that this here is going to be the square root of A squared plus B squared. And we're going to call this theta. So if we call this equal to R, so R is the square root of A squared plus B squared, which comes just from our picture here, then I can write this matrix C as follows. I'm going to actually write this as 1 over R times, R as a constant times 2 over R minus 1 over R, 1 over R, 2 over R, right? So I'm just factoring this R all the way out. In this picture, I'm going to put this as A. So A is going to be 2, and B is going to be 1. right? The positive version of this 1 minus 1. Okay, so in general, what we've got is we've got R times A over R minus B over R, B over R, A over R. And anytime we have a matrix like that, we're going to discover that this is, in fact, a rotation matrix. Now, from my picture, in terms of this angle, A over R, well, a cosine of theta is adjacent over hypotenuse. So this is cosine of theta. Sine of theta is opposite of over hypotenuse. So this is sine theta. This negative B over R is negative sine theta. And A over R is cosine theta. Now, this matrix that we've come up with over here is, in fact, a rotation matrix. It takes E1, the vector that points along the x-axis, and rotates it at an angle cosine theta, so cosine theta, and then negative sine theta, so that's a y value that goes down. So this is actually a rotation clockwise through angle theta, because the y value after E1 is negative. And then it takes E2 and pushes it into the first quadrant with a positive y value, positive x value, and a positive y value. So this, as we've done here, is actually a clockwise rotation through angle theta. We will sometimes see things where this negative actually ends up here instead. So if we would have seen something like, so we had a 2, 2, a 1, and a minus 1, we might have seen something like 3, 2, minus 2, 3. This is also a rotation, but when we go through this whole process, we would actually find that R, in this case, is the square root of 3 squared plus 2 squared, which is 9, which is square root of 13. But then, and so our angle theta is still going to be, we'd still take it from our original picture with the 2's and the 3's. Right? So we have x's, so we have 3 and we have 2, and so the theta would be cosine tan inverse of 2 over 3. Right? So theta is tan inverse of 2 over 3. But this actually corresponds to a counterclockwise rotation. So this is counterclockwise rotation through angle theta, which is tan inverse of 2 over 3. So depending on where the minus is, it will show up as either a clockwise rotation or a counterclockwise rotation. But in the end, when we have something that looks like this, where we have the same value on the first diagonal and opposite values on the other diagonal, we can write it as a scaling factor and a rotation. So let's just back up and remember where we are and what we discovered here. So we started with the matrix A. 1, minus 1, 2, 3. We calculated the matrix P, which was 1, minus 1, 1, 0, through the real and imaginary parts of complex eigenvector. We created the matrix C, P inverse AP, calculated, and found that we got 2, 2, minus 1, 1. We discovered that this corresponded to a scaling factor of the square root of a squared plus b squared, which is the square root of 5. So we scaled by the square root of 5, and then we rotated through an angle theta. So this is the square root of 5 times cosine theta minus sine theta, cosine theta, where theta was, again, where theta, so we had a 2 in the x and a 1 in the y. So theta was tan inverse of 1/2. All right, so this corresponded, because of this minus 1 down here, to a clockwise rotation through an angle of tan inverse of 1/2, and then a scaling of square root of 5. But putting this all together shows that A is P times C times P inverse. And so C is in the middle, and these are like changing coordinates from our previous sections. So this is changing coordinates through the matrix P, then a scaling and a rotation, and then changing coordinates back. So when we have a complex eigenvalue, and therefore complex eigenvector, it's actually the case, always the case, that we can do something like this, where we have a rotation hidden inside a change of coordinates. We can change coordinates, notice a rotation, and then change coordinates back. And so that's always the case. We'll look at one more like this, and then we'll be good to go with this section. Okay, so let's look at one more. We're going to look at this matrix, A, -3, -8, 4, 5. Let's find a rotation and scale matrix that is one that looks like this A, and then B minus B, or the negative may be down here depending on how we find things. Find a rotation scale matrix C so that an A is equal to P, C, P inverse. There's a lot of steps that go into doing this. We've got to find an eigenvalue, which will be complex since it includes a rotation, and then the corresponding eigenvector. So we look at A minus lambda I, which is -3 minus lambda minus 8, 5 minus lambda, 4. Take its determinant. Which makes -15. Plus 3 lambda minus 5 lambda is -2 lambda. Plus lambda squared plus 32. Save my matrix. This becomes lambda squared minus 2 lambda. That's -15 and plus 32 makes 17. Plus 17. It doesn't factor. We set it equal to 0. We see that lambda is b, negative b, plus or minus 4 minus 17 squared, or sorry, 4 minus 4 times 17, all divided by 2, which is 2 plus or minus the square root of 4 minus 68, all divided by 2, which is 2 plus or minus the square root of -64 over 2, which is 2 plus or minus 8i over 2, which is 1 plus or minus 4i. So we have two complex eigenvalues, 1 plus or minus 4i. We can take either one of those. Let's just take the positive version, 1 plus 4i, and find a corresponding eigenvector. So now we're looking at -3 minus 1 plus 4i, and 5 minus 1 plus 4i, 4 minus 8, which is -4 minus 4i, and 4 plus minus 4i, still -8, still 4, which becomes -4 minus 4i times x1 minus 8x2 is 0. 4x1 plus 4 minus 4i x2 is 0. We use our second equation as before. Notice that 4x1 is -4 plus 4i x2. At this point, since we don't have any decimals or fractions, we may as well just say that x2 is 1. So then 4x1, well, we could do that, but even before we do that, we can divide through by 4, see that x1 is minus 1 plus I x2. So that if x2 is 1, then x1 is minus 1 plus I. And our eigenvector is minus 1 plus I, 1, corresponding to the eigenvalue that we discovered earlier. So we got eigenvalue 1 plus 4i, and eigenvector minus 1 plus I, 1. We use our eigenvector to create the matrix P, which is the real part of V and the imaginary part of V, which is minus 1, 1, and then 1, 0. We saw that one before. So now we've got A, we've got P. We'll remember that we create C by saying that C is P inverse times A times P. Which we can just, we're going to just calculate that one by hand on our calculators. And what we get is 1 minus 4, 4, 1. We see our negative down here, which again means that it's going to be a rotation clockwise rather than counterclockwise. It still looks like it has the same form as before. Same values on the first diagonal, opposite values on the second diagonal. So our R value, in this case, the scaling factor, is the square root of 1 squared plus 4 squared is the square root of 17. So that's how much scaling we have. What the angle that we rotate, so we have a 1 in the x and a 4 in the y. So this angle theta, well, so actually, if you really want to match it to what we've got, since we've got 1 in the x and minus 4 in the y, 1 in the x and minus 4 in the y, here is our angle theta. And so theta will be, the tangent of theta will be 4 over 1. So theta is tan inverse of 4. And as we drew it, it's pointing in the direction that we want. So this is a clockwise rotation through this angle, theta equal tan inverse of 4. And so now that we've got everything, we can say that A is P, C, P inverse, where P was the matrix that we calculated before, minus 1, 1, 1, 0. C is this matrix, 1, minus 4, 4, 1. And then the inverse of P. And we have figured out that A is in fact, the rotation hiding inside is this rotation matrix here.